My slides are not moving. Okay. So today I'm going to speak essentially on computational pathology from a microscopy and beyond perspective. So you had that hands-on yesterday, where you have gone through a path lab and you saw different phases of it, how a tissue is prepared and what you cut through it, and then you stain it, and then you put it on a microscope, and what a microscope looks like, and what people do around over there. So what I'm going to speak is more from an engineering perspective on what are the different aspects which go around over there, some challenges and how we overcome those challenges. And primarily I would start with where that challenge lies, and in fact everything is not just a equipment challenge in its own way. There are problems from a physics of sensing point of view. So there is a lot of physics which will come back and forth, but it's not anything beyond say lens equations and lens understanding from your +2 level physics. So it's not more anything which is complicated than that. But then how I will progress is I would start around with that classical microscopy and some of the challenges we were solving around in classical microscopy, and then enter into something which is called as totally non-invasive way of investigating histology. So you don't have to take a biopsy and still you can find out what is the tissue compositions, and that's where I would end this whole thing, saying that we can in fact get all of those information without having to do anything invasively, and that's the crux of computational pathology, as I would have put the whole story around over there. So all of this work has a lot of people who have backed up in terms of funding, in terms of mentoring, contributions, and there is a lot of conflict because there is a lot of interest across for all of them. So the traditional way of looking at histopath is where you would have, yeah, that's a Wikipedia image from something from Wikipedia most likely, an age-old lab, and if you look at it, I mean, any of the government hospital labs don't look anywhere different, and this is from like late 1800s. So in the last almost 140 years of this whole field being existing, there hasn't been any massive change, other than that earlier they would be processing 300 slides in a whole year, and today they have to process 300 slides in a day. That's the only change which has happened. So population has increased, more and more people have become aware of it. There has been a growth in the number of histopathologists in the country as well as across the world, but that has not been at par with the rate at which people with a disease awareness have grown. So from something being 300 slides in a year, now it has come up to something like 300 slides in a day, and that has put some real major challenges over here. Okay. So typical what happens is you have this one person who is generally called as a medical lab technologist, MLT. Now that's a BSc program in most of the parts of the world itself. A medical lab technologist is somebody who is the one who prepares those slides and makes everything. And then this is that person who is a histopathologist, and typically these people have a MD degree in pathology. So they are trained medical doctors who are supposed to give the final diagnostic outcome over there. So the slide preparation and everything is up to here. The slide readout and the report signing off is what this person does. And these two people generally share a very good cordial relationship, because if he screws up everything, then his reporting also gets screwed up equally. So instead of cutting a thin slice, this guy cuts a thick slice. Instead of staining it uniformly, he stains it very non-uniformly. This guy might have asked for HND staining, and this guy gave him a pass stained slide, and like whatever is the stain of cytoplasm versus nucleus, everything just reverted out over there. And if you go over to molecular stains, then it's like a very different ball game. And in fact, for molecular stains, what happens is that most of the time molecular stains are not even read by histopathologists. They are read by people who have a PhD in molecular biochemistry, because there is a very whole different way of biochemistry which goes in over there in order to explain which molecules are present. And so certain stains around a certain anatomical structure would mean a certain thing, and that does not, it's not a vanilla rule which will apply to all of them. So that again needs a domain expertise, and biochemists typically sit and do. So in a modern lab, something like a Dr. Lal's Path Lab or whatever is there, SRL labs or something over there, you would also see people like biochemists. And if you order something of a molecular test, like the ones they were discussing, our histopathologists from TMC were discussing about HER2/neu and alpha smooth muscle actin and PKIE and all of these other ones. So they are typically not even read by a histopathologist, but somebody with a PhD in molecular biochemistry does those reportings as well. So it has become more and more complicated, but even before that, let's try to look into this whole process. So I'm somebody who comes from an electrical and analytical sciences background. For me, everything is a block diagram, and until I see a block diagram, I am never happy. So this was an effort which I did in order to make this whole process of histopathology look like a block diagram. So it should be a process flow. This is input, this guy gives this output that should maintain this conformal specification and go to the next input block. This is what my whole thing looks like. So what you will have is typically you have some organ on which you would like to do, and I am putting a very crazy understanding that I would like to do histopathology of blood vessels in the heart itself, okay, which is not so commonly practiced. I mean, the only time you would do it is for post-mortem investigation, and that also for legal purposes, and other than that nobody really does that one. I was fortunate to do it during my PhD for one of the investigations, but we had a lot of dead bodies and a lot of cadaveric hearts to do all of these things. Now, here what you do is you chunk out a bunch of tissue, so the thing which you saw inside that wax block. Now what happens after that is typically you freeze it, then you solidify that, and then you put it in a wax, you dry it, then you put in a wax embedding block, and then you have this microtome, and that great microtome which you saw yesterday, where it comes out with thin films over there, and you mount it up on a slide and then stain it, and this is what it would look like. This part is what is clear to you. Now what comes after that is you put it under a microscope. That is what Tangad had shown you, as well as Visoja also showed you something with autofluorescence, and then you look at images, and the images are something which looks like this. Great. Now a histopathologist's job is to change different magnification levels, go over there, zoom in, zoom out, and look at the whole thing. Now all of my interest is in this phase. I am not much interested in this whole phase, though they need to abide by certain standards, otherwise this part gets a bit complicated for me to analyze. Okay. Now here my whole interest is that what I have inside in a microscope over here is just a white light source, a box which contains a small bulb. Generally that bulb is, I mean these days people use LED bulbs, but earlier we used to have normal tungsten filament lamps over there, and such that the spectrum is somewhat similar to the spectrum of the sun, the standard daylight over there. So if you had done microscopy in your school, then you might remember that you had to take it near the window in the biolab, and then there was a small mirror which would be reflecting that. Generally it was a concave mirror, so that you get a parallel reflection of light coming down. So here we are much better off. We have a costly microscope which costs about a crore. I think today it costs about 2 crores. Which has very control. So the fluorescence microscope which you saw, this is that one. So this costs about a very nominal price, only 2 crores, nothing major. The one which was kept outside is a bright field microscope, does not have fluorescence, and that also does not cost a lot. I mean, I think that was something around in the order of 5 lakhs or something. A typical lab would have a much cheaper version of a microscope, I would say, about 30,000 to 40,000 rupees. The government never spends anything on equipping hospitals or doctors. Possibly governments are more focused at publishing big banners and advertisements on flex papers, which can now be dumped into dump yards and create more garbage. I mean that's what at least I have seen in my grown up age since I have started to vote. So this whole thing is there, but nonetheless all microscopes are almost the same. The only difference comes down in terms of the optics, and we'll come to that. Now once you have this part, then if you look at a systems process, then what happens is you have a white light box from where light is generated. Now any light will have its own spectral spread. So what I have on the x-axis, or this horizontal line, is essentially the wavelength, and what I am looking on the y-axis is basically the power of light in that wavelength. Okay. So light is essentially a bunch of photons which are coming up. So each photon will have one quantum of energy. The number of such photons falling on that surface per unit time is what is power of light over there. So there will be different photons of different wavelengths, and accordingly the power is going to vary. Now this is and this is what is called as a spectral power distribution, a power spectrum density plot for any kind of a signal. In signal processing we typically use this. So the information which it essentially says is that what is the total number of photons of a given length which is falling on a surface per unit time. This is what is supposed to be over there. Now why that is important is we essentially sense whether a surface is dark, bright or whatever based on how many photons are incident on it per unit time. So the screen is white over here, what you are seeing, this background is white. Even if I increase the brightness of my projector, still it will be white. But then where the difference comes down is the shade of whiteness which you see. So if I increase the brightness, it's going to be more whiter. If it's not that much, then the whiteness is less. Now the next point is that what happens in order to see a color. So typically you know about Newton's wheel of color. So the 7 different wavelengths on which if you had that wheel and you rotate it very fast, and then you would see white light. So that's what we are all taught, that the visible range is typically in 7 wavelengths. But then for those of you who have studied something about retina as a structure, you know that a retina is made out of rods and cones, and your cones over there are L, M and S cones, 3 different types of cones which are responsive to 3 different kinds of wavelength. And typically that's a red wavelength, green wavelength and a blue wavelength, and that's the reason why our camera sensors as well as our LED screens and everything essentially has 3 primary colors, and that's red, green and blue, and you can synthesize anything from that, and that's an additive color space. Okay. So color spaces and stuff is a matter of different interest, I don't do it in this class. But here what my point is, that if I have this light which goes into it, then the stained tissue over here is to me a block. So every single point on a stained tissue is going to interact with this light, and then essentially it's going to result in a modified distribution over here. So what this modified one essentially says is that if that location had something like a calcified tissue, so that calcified tissue is going to appear as green, appear as blue. So somewhere over here, the contrast is very low, but there are some streaks of blue in this histopathology example which you see. Now those streaks of blue are such because it lets only the wavelength corresponding to blue light pass through it, and all the other wavelengths are absorbed. Similarly, the other part of it is red because it would let the photons corresponding to the wavelength of red pass through it, and all the other ones are absorbed inside over it. Now as a result, you would see at every single point on that histopathology sample a different color, and based on what color you are seeing, you are going to infer what is the type of a tissue which is present over there. So if it is blue in color, you infer that it is calcified tissue. If it is red in color, you infer that it is fibrotic tissue. So yesterday you had seen over there, there was a purple color small dots in the middle, and that was called as a nucleus. You had a pink color surrounding over there, which was the cytoplasm. So essentially by looking at the color, you can infer to a certain extent. There are other factors obviously over there, which is the structural integrity and everything, which will be important in order to infer whether this is in a disease state or this cell is in a healthy state over there. Great. Now that this happens, let's look into what is there inside a microscope which would make that happen. So in a typical instrumentation of a microscope, what you have is a light source at the base over here. There is something called as a field diaphragm. Now the role of this field diaphragm is pretty simple. If you have a bulb and there is light coming out of the bulb, that is going to spread everywhere uniformly. Okay. But here, if I have something placed over here, I would like a parallel beam of light to pass through this one. So there needs to be some way of concentrating all of this light which was otherwise spreading into a parallel beam. Yes or no? We need to do that. Now the point is, how do we do that? So one simple example, very simple way, and which is what is used over here is, if you have a lens and you have a light source at the exact focus of this convex lens, whatever comes on the other side is basically a parallel beam, and it's from the other way around. So basically, if there are parallel rays which are incident on a lens, then everything will be convergent on the point source over there, which is the point of focus. If I place a source at focus, then it will again use the same rectilinear propagation of light concept and make a parallel beam. So this bulb is situated over there. You have a lens which essentially makes a parallel beam, and that comes over here. There are other things like a condenser, then a diaphragm for adjusting the condenser, and the job of that one is basically to thin or thicken the beam size. So whether you want a very thin beam like this or you want a thick beam, so what you would have is, you have a circular aperture, you keep on turning that, and that will close it or it will make it open. Okay. Very straightforward way of controlling that one. So first I make that parallel, and then I control the thickness of that parallel thing over there. And from there over here it goes where you place down the slide, and on top of it you have something which is called as an objective. You saw those cylindrical lenses over there which were being turned on a microscope yesterday, and that's an objective. We'll get into what is there in an objective. It's typically made out of number of lenses inside over there, and it's a compound lens which is present. Now from that objective, it goes over here into something which is called as an observation tube. So here also you have some lenses in order to magnify. and you have a camera tube where you place that extra camera from where you get a feed onto your PC monitor. Otherwise, you will have to look through those binocular objectives over there. Now, other than that, it has some power supply, some intensity control for the lamp and everything. So, you are able to control the size of the beam, but if I want to control the intensity, which is the total number of photons incident per unit time, then I will have to change something on the intensity of the lamp itself. So, there is a separate power electronic circuitry. Now, if somebody studies embedded systems or anything, you might know about something which is called as a pulse width modulated control, and a PWM is a very standard way by which this circuitry works in order to control the intensity of a lamp. Okay. Not much of rocket science. In fact, building a microscope is such a trivial matter. If you know your +2 level physics very well enough, something from your engineering optics, whatever you have studied, a bit of engineering mechanics and understanding of a workshop, and a bit of embedded systems in your second year or third year, you can pretty much build your own microscope and sell it for 30,000 rupees. And making a microscope which sells for 30,000 rupees would cost you the order of something 5 to 10,000 rupees itself. The bill of material, paying your salary and your establishment electricity cost, your trade license cost, and whatsoever over the table and under the table dealings of finances you will have to do in order to run a business, together that will make that one suffice it within 10,000 rupees, so that you can pretty much sell this microscope to a marketing guy for 20,000 rupees, who is going to sell this in the other market for 30,000 rupees. 10,000 rupees because he has been able to sell and you are making money. That's his advantage. His part of the money making which he is able to do. Now that we have this part, let's look into what happens within a magnification funda typically. Okay. So this is from one of your old lens type understanding of it. So if I have a lens, I have an object over here, and then that projects something into my eye and I am able to see that. Now the farther an object is from the lens, the smaller would be its image which is casted on my eye. So accordingly I would see that as smaller. So if I want to increase my magnification, essentially I will have to bring this object closer and closer to the lens. Right? Now look at this thing. For all our practical purposes, we were assuming a lens to be a flat plane. But a physical lens is not a flat plane. It has a bulge in the middle and it tapers in the sides. So obviously there is a limit to which you can push your object closer to the lens, and the closest you can put an object to the lens is that bulging part. Anywhere closer to that you will not be. So essentially an optical magnification will also hit a limit at a point of time, and in fact what also happens is that lenses which have a higher magnification factor, which essentially is also dependent on the focal length over there. So a shorter focal length lens will have a higher magnification factor, and a shorter focal length lens which has a higher magnification factor also has a higher curvature, which means that the bulge is much more over there, so that restricts itself. So now you can see that it's a counterbalancing problem over here. I can really magnify higher, but if I have a lens which magnifies very high, then the thickness of that is so high that I cannot really bring it anywhere closer to the principal plane over there. I am physically stuck over there. So this is one of the major problems you are going to have. Now in order to get rid of that, these guys are very clever. What they did is, let's try something else, which is called as a virtual image and a virtual magnification. So if I have one lens that is going to cast an image somewhere, I take the other lens and place it such that the object of the image from the first lens becomes the object plane for my second lens. So I can now cumulatively keep on stacking more and more lenses which are thinner and also of lower magnification factor, but because I have stacked a lot of lenses, I can get a cumulative magnification factor which is very high. Shall be able to do that, right? So that's what happens within an objective over here. So a typical objective is something which looks like this. You have seen that steel one underneath the microscope over here, and then it has a lot of specifications inside over there. So it typically has a lens over here. There is just a collimator, a flattening lens. I mean, that's something like a zero power lens on your eyes. Some people wear eyewears which don't have any objective magnification power for safety purposes or something. So there is something over here, and the whole purpose of that one is to prohibit any dust from entering inside. Otherwise that creates a problem. Now there is one lens over here. There are multiple lenses inside, and it's a stack of lenses. If you have a higher magnification, you would also see that that lens keeps on becoming bigger. So if you recall something from yesterday, in that particular microscope, the 100x objective was the tallest, the 10x objective was the shortest over there, and that's because you are not able to, in a 10x you will not have to fit so many lenses, in a 100x you will have many more lenses which have to be fixed in. So that controls this turret length over there. Now that I have this, there are certain specifications for any of these kind of lenses. So one of them is the first part, which is magnification factor, and that's very critical. So this over here is a 63x magnification lens, and this I think for most practical microscopes 63x is the highest magnification which you can achieve with something which is called as a air based objective. Beyond this you will have to go with a liquid immersion. Now the difference between them is that I have a cone of light coming over here, and then it hits a surface of a lens. Okay. Now whenever light is coming from one refractive index to another refractive index, it's going to propagate, plus it's also going to reflect following the critical angle principle over there. Now because you have a higher curvature, so you have a higher chance of that it will be obeying critical angles and getting reflected for a higher magnification lens. Now as a result of that, what we can do is, in some way, if you don't let the refractive index of that lens change. Now the problem is, the only way of not being able to change the refractive index of the lens would be by making the lens go up to the level of the slide itself or fit on top of the object. Now imagine you put some cell, are you going to put molten glass on top of it? That's the only way. Glass's refractive index is glass's refractive index, but you are not able to do that. Now interestingly, coconut oil or cedar oil, these kind of oils have a refractive index which is the same as glass. So next day you can go and do an experiment. You take a glass, you fill it with coconut oil or cedar oil, and you would see that there is no reflection, there is no refractive change which essentially takes place over there. That's an interesting point which we can observe. So that's a principle which is used over here. So we put a drop of oil over there such that this lens fits around that oil, and then you have a continuous cone. Okay. The next part which comes down is a focal correction. Now what this focal correction essentially means is, what is that farthest point which is always in focus, or wherever you look at any object, where does it appear to come from? Now these are all infinity corrected lenses. Now an infinity corrected lens essentially means that whatever I look through that lens would essentially imply that as if the object was at infinity. Okay. Now when does the object look as if it's in infinity? When the just the prior virtual image which was cast, that was cast exactly at its focal point. Then it will become a parallel ray after this one, and that will appear as if it's in infinity. So that's the thing which comes down over here. Next you have something which is called as an optical aberration correction, and that this one particularly is called as a neofloor. Now for optical aberrations you need to remember that a lens, you can assume a lens to be made out of say two prisms. Say a triangular prism where your bases are cemented together. That is almost like what a cross section of a lens looks like. Now when you have a prism and you pass a parallel beam of light, white light, you would see the whole spectral distortion happening over there. So you would have one part of the spectral distortion happening on the top prism, one part of it happening in the bottom prism, and then they would meet. So essentially, although you are sending a parallel beam of white light through a lens, on the focal point it will not be a parallel beam of white light, there will be a spectral spread. Now you can in fact do this experiment. So if you take a magnifying glass, the reading glass which you have, so that when we were kids we used to do that, hold it under the sun and then see a piece of paper burn, or put a matchstick and then see it burn, and there were some of us were too cruel, so we would also be incinerating some other living beings as well. That's a part and parcel of growing up. So you incinerate some living beings in the early part of your life, and then those living beings come down in the darkness of the night, and then they start incinerating you mentally in some way. So now in this whole experiment, if you look clearly, your physics of rectilinear propagation of light clearly said that you need to have a point. You will always get a point when there is a parallel light. But when you were focusing that one, you would never get a 1 point. You can pretty much move that at least an inch up and down, and still you would see that there is a small bolus which creates a small blob kind of a thing. And that is essentially happening because every wavelength is not at same focus. So when something is focusing over there, there are others which are not focusing. It becomes out of focus, and that's the whole reason, because you had a spectral spread. So along a depth there was a whole spread which comes down. Okay. So these things are special coatings of chemicals which are placed across the lens so that your white light after all of this is still white light at that point itself. And that's really critical for us to look at. So there are par floor, there are floor, and there are neo floor, there are achromatic, apochromatic, different kinds of lenses based on like whether they are able to balance for all red, green and blue wavelengths, or it's balancing only for the red and green and not compensating for blue. These different aspects are there, and the more compensated a lens is, the more costlier it becomes. And that's, you would also see that present on your camera lenses, and that's the reason why people would say that please don't wipe your camera lenses with shampoo or detergent or ethanol or benzene or even what is that cleaner for glass? Colin. Don't even use Colin on that. And some of us wear expensive eyeglasses. I mean, today if you go on say Titan Eye Plus or these guys on, what is that online store for eyewear? Lenskart, yes, I get from Lenskart and I still keep on forgetting. So on Lenskart they give you lenses which have specialized coating, like my lens has a specialized coating for me because I have a very high power lens. So the thickness is supposed to be wide and I will get down a lot of optical spectral distortion. So essentially white lines to me should never be white, they should be full spectrum of rainbow coming down over there, but I have a specialized coating which prohibits that. Now that increases the cost. You would see that your just around the corner lens maker who makes it with glass would make a spectacle for 300 rupees or 400 rupees, whereas the Lenskart one is going to cost you 3,500 rupees, and that's where the difference comes in, these extra coatings. And this is a critical part of it. So I said that whether a lens can be only in water or if I am immersing it in oil. Now look at a problem. If I am immersing it in oil, I solved all the problems around with refractive index, but then I also introduced more problems because that oil is going to seep inside the lens. The moment it seeps inside the lens, if water seeps or oil seeps, now there will be microbes, bacteria, fungus and everything which starts growing inside over there, and then your lens becomes corrupted because they are going to obstruct all the light which comes down over there. So these lenses again are something which have a jacketing over there to make it waterproof completely. So you have waterproof watches, you have waterproof cameras, waterproof lenses and everything, and then they are essentially somewhere where around the lens with that joining of the glass to that metal cylinder, there is a specific coating kept such that water cannot seep in through any of those pores. Water is a very small sized molecule, I mean the smallest size molecule ever available that can seep through anything. And now imagine you are trying to make a coating such that a single molecule of water cannot also seep in over there. So that's itself a very big engineering challenge. Now comes this major important part of trying to look into what happens as I keep on increasing magnifications, and also there is that issue of the focal change which is happening over here. Now we have a specific thing which is called as numerical aperture. Okay. So what numerical aperture essentially is, it's in general it's called as n sin theta, where n is basically the refractive index of the media in which you would see this light diverging, and theta is the cone of this angle of light divergent which enters into the lens over there. But then in typical sense, this is also a ratio between the aperture of the lens, which is the opening of or the beam width which is incident on the lens, and the distance between that principal plane of the lens to the focal length over there, and that's a constant number for any kind of a lens over there. Okay. So the highest number is constant. So typically what we try to do is that say for this particular lens at this particular position, you will have a certain numerical aperture which is 0.25. Okay. For this particular lens from this position, you will have a numerical aperture which is 0.90. Now what will happen is, say on this lens which has a numerical aperture of 0.25, I take this sample which is this close and place it over here. Okay. Now the moment I do that, because this sample is exiting the light at a much higher angle, so this is typically exiting the light at a 64-degree angle, whereas this one is exiting at a 15-degree angle. So that 64-degree angle will have a significant part of the light which will just go outside the lens. It will not even fall in the lens. So essentially I am going to lose a significant part of my intensity over there in total. So that's another rule which you need to really adhere to, which is you will have to change the aperture over there so that the maximum aperture control matches that the numerical aperture of the lens itself. And in fact, typically when you have a manual microscope, so yesterday you saw some of these automated microscopes, like you click on one, so what that click does is it will change the lens, it will also rotate the aperture control and fit it down over there. So there are 2-3 things which you will have to control, and one click solves all of them. Whereas if you are doing it on that manual one from Leica, then you have to change that, plus you will have to change the aperture as well. There was an aperture knob which they were changing if you were very observant over that. And then this is really needed. Otherwise what happens is that you would see that your sample is still the same, you just change the lens, but everything became darker. So this has to really be taken care of. From an image resolution perspective, this has a very important implication. And in fact, that's where now I am entering into what I have to say. Till now it was not yet anywhere closer to what my main problem which I am trying to solve over here is. So here in this case what happens is, if you have a low numerical aperture, something like a 0.20, versus if you have a very high numerical aperture like 1.15. Now what this typically changes is, when you have a very high numerical aperture, you have a lot of light which is coming, things are very much closer to your lens, and as a result of that, 2 points in space. So resolution is typically defined as what is the physical distance between 2 points in space which can be discriminated as 2 independent points. That's simple definition of resolution. Okay. So the moment your numerical aperture increases, because you have it closer to the lens, since your magnification also increases as a result of that, you will be able to discern very effectively between 2 points which are very much closer. Okay. Now there is another con associated with this. I've been able to very easily identify 2 points which are very close by and discriminate between them or resolve between them. The problem comes in that because I am much closer to it, so I am able to focus or I am able to image only a much smaller section of my slide. My slide might be this big, I am able to look only at a smaller region. Whereas if my lens is very far off, so it's again that bird's eye view versus closer view problem. So if you are on a close-up, which is at a higher magnification, you look at a smaller part of the region. So now if I have to image everything on the slide, then I will have to take more number of images, I will have to look through more number of scans over there. Whereas if I am at a bird's eye view, much far off, my numerical aperture is low, my resolution becomes low, but I am able to scan over a larger part of that image, and as a result of that I will have to look through much lesser number of spots on which I will have to scan through. So that's a trade-off which has to be taken care of. And typically how pathologists do it is that they would change between these lenses over there. So yesterday like we were doing it on a 10x, which was called as a grossing survey. So you scan over it very fast and you find out which regions have sort of abnormalities and some tissues to look into, and then you change over to 20x or 40x of a magnification and then look into that particular cell or intercellular spaces over there in order to find out more details of it. So that's a manual way of changing it, but nonetheless this problem is still there because it's a counterbalancing problem in itself. So you can resolve higher, but then you will have to scan more. You can scan less, but in that case you will be resolving lower over there. So whether I am interested to look into the whole tissue structure versus I am interested to look into only the nucleus is where I will be having to trade off between my numerical apertures appropriately. There is another issue which comes out along with this numerical aperture, which is essentially called as a depth of focus. Okay. So because your angles, so look at that same thing about a lens. So your light, which is white light over here, that is going to spread across over there. Okay. Now typically it's going to be in focus somewhere over here. This is the point where everything is convergent. Okay. These are the places where it's not convergent, it starts becoming divergent over there. But the point is, when you look at a sensor, a digital sensor is placed over there. A digital sensor has a fixed size. So it will have some 10 microns cross 10 microns. Now if 10 microns is from here to here, then whether the light is incident over here versus here, everything is going to cast itself as one single pixel itself. What that would mean is, if I keep on moving my sensor from here to here and back, my image is still going to be in focus. It will always appear as if the whole image is in focus because your sensor is not able to resolve anything any further. So if I have an infinity resolution sensor, I could have gone down to this point, which is a point which is tending towards 0. Otherwise, I will always have this finite amount of resolution challenge which will still keep on coming over here. Now that gives us a very advantageous situation in microscopy. I don't have to keep on continuously tuning every single position to come to that point of focus. I can pretty much be over here, this is also in focus, over here this is also in focus. Now that reduces the workload significantly because you don't have to move your lenses up and down and keep on refocusing and recorrecting the focus itself. That saves a lot of time. Okay. Now for a high numerical aperture lens, this whole window in which you can change everything is much smaller as compared to a low numerical aperture window which will have it. Now as a result of that, this is just an example in order to show you like what happens with that. So here we have 3 bundles of thread which is placed over there under a microscope such that this focal plane is somewhere on this red thread. So red, you can see these individual strands over here easily, whereas on the yellow which is behind it, so yellow is somewhere over here and blue is somewhere over here. You are not able to discern between them. So now if you want to do that, you can obviously keep on changing the focus over there. Now the point is, with a high numerical aperture you will be able to focus either on any one of them, not all 3 of them together, whereas with a low numerical aperture you will be able to focus on all 3 of them together. Got the point? Okay, clear till now? Now there is another kind of a microscope which is called as a reflected microscope. So what happens in the earlier case, what we said is that there is a light bulb, there is a sample, light comes from here, passes through here and then you see it. But say that this surface is opaque. In that case you will not be able to see that. Then the light has to come from the top, reflect and go back. Now when the light comes from the top and reflects, that means that the light is coming through this objective itself over there. And there is a specific engineering which has to be done in order to let that happen. And that's something which is called as a reflected mode microscope. Now a reflected mode microscope is also something which you use in fluorescence. So you have something called as a fluorescence lamp or a lamp source. From here the light comes in, goes over here, and then from here the reflected one comes over here. There is an optical beam splitter over here which leads to a point such that any light coming from here will reflect only over here. It's very simple. If you have a glass which is at 45 degree and you have a parallel stream of light coming down, it will all get reflected over here and nothing more. It will not do like this. So it just goes from here. And from here whatever comes over there, some part of it will be reflected to the light source, rest everything is going to pass straight. Now whatever is reflected to the light source, there is no sensor over here, so it's not going to burn. I mean, this is the same example as like you have a bulb and then you shine a torch at a bulb. You shining a torchlight at a bulb is not going to fuse the bulb in any way, nothing goes wrong over there. And effectively it does not change the intensity. But then you are looking through a smaller lens with a smaller light source and you shine a torchlight on your eyes, then you will be blinded. So that's the whole issue which you will have to take care through this clever optical design over here. And then that's what I was telling. So these designs are not that complicated. You can pretty much do that on your side itself. For fluorescence microscopy, the extra other thing which you have is basically something which is called a fluorescence filter. So yesterday you saw that there would be either a red wavelength light or a green or a blue, something over there. The way we do it is you have a set of filters which are rotating and then you would choose whichever filter and that's going to basically source that light. Similarly on the reflected light also you put down some specific filters so that you are able to filter only that particular wavelengths which will pass through it, and then you see these images like here. So these are about some mitochondrial structures if I remember it clearly, and you have these strands of in the green fluorescent protein, in the blue fluorescent protein and the red fluorescence levels which are seen over here. So those details are what we had covered yesterday and we had shown you exactly what it works. This is about how that particular microscope works, and typically any fluorescence microscope will have a reflected mode. It does not work in a transmitted mode. The reason being that you cannot have this kind of a bigger bulky setup somewhere placed closed over here. So there are some exceptions, people build their own transmission fluorescence microscopy as well, but in general a commercial one will always be a reflected fluorescence microscopy system. In a modern practice and what happens in today's lab, so there was something which Dr. Debdoot Sheet and Dr. Deepak Mishra were telling about, which are called as whole slide scanners. So you have full bulk of battery of robotic scanners. What you do is, this is a small cassette loader. In that multiple slides which are all stained are put down in a cartridge kind of arrangement, and then you load this cartridge over there. So there is a robotic arm which picks up one cartridge, puts it under a microscope, scans it exhaustively, makes an image out of it and stores it. So you get a workstation in which you have all of these slides. You click on one slide and then you keep on like moving your browser window over there and you would be seeing through it. So this is a desktop viewer of all the slides available over there, such that the pathologist now does not need to anymore sit at the actual microscope and look into the objective lens and look. So he can pretty much just focus on the desktop screen over there and do his work. And this has enabled a lot on telepathology. So pathologists can now be vacationing in Hawaii. They can still look at it. And I guess pathologists make enough of money to vacation in Hawaii. Otherwise the costs of Hawaii tickets are quite high. Or you may be struck in the heat of Indian summers and still work from your home. So these are big advantages which happens. In fact, that has ended up opening this whole service chain of telepathology, where there are these hospitals in Europe and US which don't have enough number of pathologists over there to do it, and by law they are mandated that every slide needs to be scanned by 3 pathologists and then you give a majority voting in terms of the decision. So what they do is they have one pathologist over there, they get it read by that guy. Then they ask 2 more pathologists in India and say that I will pay you some 2000 rupees or 200 rupees or whatever to read this one slide. Oh, it depends on hematology slide is 200 rupees, nothing more than that. You have a histopath slide that is going to cost you 2000, 5000 or something over there, and then you see that you are going to make a good amount of money by just reading one slide. Otherwise your 5000 rupees is what? You need to read 50 slides to make 5000 rupees possibly in the other case of. So that has opened up all of these avenues because you got down these kind of scanners over here. Okay, so my story is more around what we did with one of these kind of scanners which a company in India was trying to build up, and how we solved that one. Now, what happens when you are able to digitize that is something of this order. So an image of a histopathology sample typically is in this size. Okay. Now look at the file size, that is 65 GB. We are not calling MBs or anything. I mean, it's 65 gigabytes, not bits, bytes. So now imagine, this is like a few thousand times bigger than the largest photograph taken from a camera. Even if you do a panoramic photograph of this classroom, this is a few hundred times larger than that panoramic photograph itself. And that's where all the problem now creeps in. What do you do with this? Like, where do you store? First and foremost question. So it's like you have a slide. In order to store the image of a slide, you will need a pen drive which is larger than the size of a slide. So now let's get back to the old problem, archiving. How will I archive? So in order to archive that, I digitized. But after digitization, I would need more amount of physical real estate which is larger in size than the size of the slide itself. Can I archive? Now do a very simple thing. It's a 65 GB thing, and I have say 8 slides. That is going to be about 500 GB. Now what is the size of a 500 GB hard drive? A 2.5 inch hard drive is also this small, okay? But that has a physical size which is much larger than 8 slides kept one above the other. A 100 slide box, 100 slide the cardboard box in which you get the original supplies is smaller than the size of a 2.5 inch hard drive itself. See, we wonderful technology, guys, and this is like Japanese technology, that is the world lives in 2020, Japan lives in 3020. So this is that level of engineering which now created a bigger problem. And Japan is already landlocked and starved of land. So now what do you do? Huh? On a cloud storage, you are not giving it over to the physical clouds over there. That is still a hard drive at a data center which sits somewhere. That's going to take some square feet. Do you know how a cloud storage works? Do you have any idea how a cloud storage works? So cloud storage is still a hard drive. The hard drive is just not connected to your computer. It is connected to somebody else's computer where you are doing. But you would still need that physical hard drive. Now my point is the hard drive is going to reside somewhere on planet Earth and I am going to eat up that space. Either it's my space or somebody else's space, but I am going to still eat it up, right? And if you are somebody of a logical human being, you need to think in terms of the whole planet Earth. You cannot start thinking, no, it's not eating up my space in my room, so I am not to be worried about. Because if that is how our thought process goes, then everybody else will also be thinking, that's not my problem, that is his personal problem, let him deal with it. That's not how human civilization ever survives. You will have to take that global picture into consideration now over here. So now here gets that bigger problem that you have been able to digitize and you created a bigger problem as a result of this digitization. Okay. So what do you think, what can we do? Some ways. Compression. Great guy. I mean, this guy keeps on hearing compression day in and out in the lab and now his brain just goes compress data. In fact, you can compress data, but then you will have compression related artifacts. Yes, what you told is very correct. I mean, we basically chop off all of these. In fact, there is no data stored corresponding to these white regions. So how it is stored over here to make it to 65 GB is not all pixels. So all relevant pixels over here are only stored. Everything else is a white space. So there is something which is called as a MAT, M-A-T, not a map. A MAT, not M-A-T, M-A-T-T-E, a MAT. So what this MAT does is it says whether there is something visible over here or there is everything is useless over here. It's a 0101 binary map over there. Now that binary map helps me in saving a lot of real estate, and then I can say that only these places are where there is something useful information, and then it behaves like a linked list. So you can have every position and then link it to which is the next position, and then you keep on storing that as a linear string over there. So that's very simple, like PDS lab level assignment which is done in order to create this file structure over here. Still the problem is that if you have more number of pixels, you are still going to have more amount of space requirement over there. Now the question comes over there that can I reduce that? So that's what we have done. So we have put down some image processing that has analyzed that these are the regions where there is some useful information. So we store only them. Rest everything is dropped off. So the moment you extract some information out of it, the image does not remain anymore an image. So it's going to be something else. Now for a histopathologist to infer, he would need something like an image. And it had taken us almost 25-30 years to make them come to a point where they are okay to browse an image on a browser on a screen and tell, instead of looking through that optical binocular eyepiece over there. And I have lived through that. I've been doing telepathology system building. Like I built my first microscope when I was just in my first year of master. So, and that was more than a decade ago. Now, like at that point of time, you go and tell a pathologist to actually look on a computer screen and then analyze images, and like first thing is, look, I'm not doing that. I cannot. And they used to make real huge errors. Like, unimaginable amount of errors they would make by doing all of that, and you put them on a turret and they are very happy to do, and everything is correct. Now from there, a decade later, now they are much more comfortable. I mean, now I have friends in pathology who just browse it on their phones. I mean, they have iPhone browsers and then they just browse and make a inference on top of it and tell it. And then you lose the color, and then all the information was in the wavelength. So see, essentially you can bring it down. Whatever you do to bring it down, you are going to lose some information. Another problem is that can I have some way in order to recreate this information, right? And that's where all of my jugglery lies. So I'm sort of like a well-established guy to recreate information, and that's what I do to make a living out of it. So this whole story is about that we acquired images in a very low resolution such that this whole pixel space is much lesser, and then what we did is something called as a super resolution. So essentially 1 pixel I will map it onto 4 pixels, a 2 cross 2. But then if you want to map a one to many function, all of you know that it's a intractable way of mapping something. So if I have say 4 numbers, 1, 2, 3, 4, what is the average value? 2.5. Okay. Now if I give you this 2.5 and then I tell you, can you recreate the 4 numbers from where 2.5 came? So one possible option is 1, 2, 3, 4. Another is 4, 3, 2, 1. Another is 1, 3, 4, 2. Another is 1, 4, 3, 2. There can be another option which is 2.5, 2.5, 2.5, 2.5. There can be another option which is 2, 2, 3, 3, 2, 3, 2, 3, 3, 2, 3, 2. There can be n number of such options which can happen. Now imagine that's what is typically called as an intractable problem in mathematics. So you are given something, from there you have to derive something else, but whatever you derive on the other side, you will have a set of possible solutions which obey, like from that output also you can come to this input, but you don't know exactly from which output was this input derived at any point of time. And that's exactly what happens in a super resolution problem. So from 1 pixel I want to create 4 pixels, but then what will be the value of those 4 pixels? Exact value of those 4 pixels is where the question now lies. Now why do you need that? Because if I make this whole image into say half of this one, so 97, if this was 98 then that would be 49, so some 49,000 cross 110,000 pixels over there. So essentially from a 49,000 cross 110 pixels coming down to this particular location, every 1 pixel will have to be mapped into 4 pixels, otherwise that will not happen. Now until I am able to very accurately map, I will not be able to resolve between those 4 pixels. So I will have more number of pixels, but my resolution will not increase because I am not able to resolve between 2 points over there. So this is the problem which we are trying to solve over here. Now if you look at any standard sort of a whole slide image, this is for one of them, what you would see is that there are different regions and then they have different kind of behavior. So there would be different kinds of tissues present at different, so this will be one kind of a tissue, this will be other kind of a tissue, and this is where all the interesting substance lies. So some of the places will, if you look into the neighborhood, you can always make an assumption that in this neighborhood, in the low resolution, if it behaves like this, in the high resolution the neighborhood should be like that. And this is where all of machine learning comes into play, where we essentially try to derive this knowledge of what low resolution manifests into what set of a high resolution. And now given that you have ample amount of data surrounding this one, you will be able to derive this 1:1 transformations. So this is about understanding of what, like how things would change from one level to the other. So this is typically what's called as a multi-resolution pyramid. Okay. So I can have images at something which is called as a 1x magnification, which is essentially just looking at the same thing. I magnify it 10 times. So it's essentially the same object which is present over there, but what I am able to do is I am able to much easily resolve between 2 neighboring points in there. So whichever 2 points were not resolvable over here, I am able to resolve it over here. Similarly, as I go from 10x to 40x, I am able to resolve it even more over. So now 1x to 10x means it's a 10 times increase in terms of area. A 10x to 40x means it's a 4 times increase in terms of area. And if it is isotropic increase, which means that on all the axes it will increase in the same proportion, then in the x-axis it will increase by twice, in the y-axis also it will increase by twice. And that's how you go from a 10x to a 40x magnification. And now these are 2 of those images at 2 different magnification. This is at a higher magnification, this is at a lower magnification, in order to look into them. So the work which we did was along with this particular company called as SIG-tuple, and the whole idea was that if I am building a robotic microscope over here which is going to acquire images, now it cannot digitize the whole slide in one shot. So it will have a particular magnification. At that magnification it is going to take a set of small patches. It will synthesize all the patches through a registration process, like it will integrate and stitch all the patches in order to create this big 97,000 cross 220,000 sized block of image over there. So if it's at a higher magnification, it's looking at a lower area. Higher magnification, lower numerical aperture, higher magnification, higher numerical aperture, small sized area over there. So it will have to take more number of images. Now see, in order to take an image, when you take it with your camera, you have to hold your camera still for some amount of time, then press the shutter, then again hold it. It will take something which is called as a shutter integration time. It needs to collect enough number of photons and then go to the next image. So my number of images I am taking, if that increases, then my total time to image this whole slide is also going to increase, because there is a finite amount of time which I take to image every single point over there. So essentially, say if I am imaging at a particular magnification, say 40x, and I am taking some 30 minutes of time in order to do that, if I am now able to image things at 10x, then I will need to take in 4 times lesser number of such images, because my area increases by 4 times. So my total number of patches I will have to take is 4 times lesser. So my time is also going to reduce by 4 times. So that becomes 30 divided by 4, which is approximately just less than 8 minutes. So now my imaging process becomes faster. The only trade-off which I had is I lost out the resolution. So that's something which I will now have to compensate. So this super resolution and a computational way of super resolution essentially which was brought in order to do that. So we could now deliver a product which for the company works very fast. So their AI engine and everything takes about roughly 5 to 6 minutes in order to read and analyze a whole slide image and give a report, and we are able to acquire images in the same order in which an AI inference engine runs. And that would pretty much make it as a seamless process. So you put a slide, the slide is digitized, while the next slide is getting digitized, you have the AI run the whole report and you have a printout of it given. So essentially in 16 minutes you will have an exit, and there is a 8-minute per phase of a pipeline which you are creating over there. So it becomes a very streamlined process. So you have one slide going in, you know that the slide goes in, 16 minutes later you have the printed report out. The next slide goes in, 16 minutes later you have a printed report out. You are not able to, you don't have to wait for 30 minutes. So now how does it change on a bigger size of it is, earlier if I was able to scan a slide in 30 minutes, right, then in a whole 8-hour work day I will be able to scan 16 slides. Half an hour per slide, maximum 16 slides in one machine. Now that I have increased it to 4 times, so now that 16 becomes 16 into 4, which is 64, which is a substantial larger number over there if you look into it, right? So these are points which play a very big decision in terms of when you are trying to design a product. So let's get into how we did that. Now a typical way is, everybody does deep learning, so we also did deep learning. We also took a CNN. Okay. So if you are not very happy around with CNN, still we cannot do anything, you will still have to take a CNN. Okay. So the idea was, you take a low resolution image which is essentially at 10x objective magnification, you feed it through this CNN and you are able to get some image which looks as if it's like at 40x. Now the point is, this CNN over here is not something which you can just buy off shelf or something where you can write your own codes and do it. That has something which is called as a trainable amount of weights, and this has to be taken care of, and then that's not a trivial problem, that's a bigger problem. So what this leads is, I told you that different regions will have different neighborhood characteristics, and if I can somehow relate that, so given a large amount of data I should be able to relate that and create this knowledge base. So training a CNN is essentially going to do that. It's going to create that knowledge base, that if I am looking into my neighborhood in a low resolution it looks like this, then my high resolution neighborhood information should be of this other type over there, and that's what I am going to do over here. But in order to know about that, I cannot do this in an open-ended way, such that I give a low resolution, I get a high resolution, and then I say it's okay, because I don't know exactly whether that is the high resolution which it should have. So now for every 10x I should also have a 40x equivalent over there, which is a real image which comes to me. Now what I am going to do is, every time I get something generated, I compare between these and this, and the comparison is very simple. In plain Jane signal processing language, that is something which is called as a mean square error. So what you do is, you have 2 pixels at the same location, you compare their value, and the best way of comparing them is you basically subtract their value and then square it, and then take a summation over all the pixels which are present over there. So if the output image is the same as the input image, then this thing is going to be 0. So if every pixel in the output image is the same as the input image, so at every pixel the difference is going to be 0. So if I square 0, that is also going to be 0. If I take a sum of all the zeros in a matrix, that is also going to be 0. So in my best case, this error is supposed to come down to 0. And that error is what is mathematically defined as something called as a reconstruction error, J-recon. Okay. Now there is some part of the error which needs to be fed to this CNN in order for it to understand. So initially this will not have that all reasoning properly ingrained in it. So what you will do is you will find, so you pass this low resolution image, you get some high resolution one, and then once you get that one, you compare it with this one on a pixel to pixel basis, and then you see that okay, there is some error which is pertaining, and then you tell this CNN that see there is some error which is there. Now I am passing you this information which is called as nabla J-recon, that is also called as gradient of this particular error, because this uses something which is called as a gradient descent optimization method in order to do it. So I mean, has everybody done some course in engineering mathematics? Yes, right. So you remember something which is called as roots of a function. So you can numerically derive roots of a function. So the way of numerically deriving root of a function was you start with a guess, and then from there you take some look something at its left or its right. Wherever you see that there is a change in sign, then you take these two pair and then you find out what is the slope. Along the slope, wherever it cuts down, then you have the next intelligent estimate, and you keep on iterating between these averages, and some point of time you will come down to almost a 0, or at least lesser than your epsilon tolerance over there. So this gradient optimization also does the same thing. A stochastic gradient descent or stochastic gradient descent, conjugate gradient descent, all of them follow a similar kind of a norm of coming down to a point such that the difference between this and this comes to 0, and that is my root of that equation. So the equation is that I am able to produce this one, and root of the equation is when these two happen to be 0 over there. Okay. What it turns out is not so trivial. The problem is that there are these things which are called as WBCs, which have a lot of detailed texture inside over there, and there are a large number of RBCs which are much smaller in size and which are very flat. Plus there is a lot of place which is just white, you just have light coming through it. Now any flat region, its average value is also going to be a flattened one. So 4 pixels which are all white have an intensity value of 250 will map to 1 pixel which is of 250. So this 1 pixel you map it to 4 pixels, that is anyways of low error. So what is that big deal over there? Now when you take an average value over this whole error metric between the super resolution SR and the real, where majority of the places, because they were almost flat, they gave you 0, then you tend to believe in the average case that my error is low. So here also that is the same thing which happens. So your error can go low, but these textures will not be reproduced properly. And that's where all the problem lies, because I have very small number of objects which are the most critical, and the whole diagnosis was around this WBC, it was never around RBCs in any way. The only thing you are going to do around RBCs is whether they are morphologically correct and whether there is sufficient number of RBCs per unit area or not. Beyond that there is no interest. WBCs you will have to categorize whether there are those 13 types of WBCs, what is the ratio between each type of WBC, what was the shape of each type of WBC, whether one went up, another went down or not, and that really impacts your diagnostic quality, whether you are taking a favor whether you are giving a decision in favor of a certain diagnostic routine or not. So you cannot compromise on that image quality in any way, and that's where the challenge comes. So whatever was lesser in count is the most deceiving one, which needs to be more accurately captured over here through the super resolution process. So what we did is we designed something which is called as a Turing test. Okay. So how many of you have heard of this gentleman named Alan Turing? 1, 2, 3, 4, 5. Okay. So what is Alan Turing famous for? Louder. And there is something called as Turing test. Has anybody heard of that? So what is a Turing test? Yes. So essentially if there was so this was the basic test of AI. So it was what Turing had formulated was very simple. He said that artificial intelligence would exist. That is what he said. Only at the point when a machine answering to a human's question will get the human confused to believe as if there was a human who is answering to his question. So the fun part is that he coined all of this somewhere in early 1940s, and it took you almost like 2018 in order to get Alexa and Siri speaking with each other and actually quarreling. So that was the only point when we could break the Turing test, and anywhere before that we have it. AI in its whole existence has been so tardy and so slow, it took it almost how many years? 60, 70, 80 years to break the Turing test. Very complicated test and a very dangerous professor. So imagine that test comes in your semester examinations. You are pretty much doomed. Like you try for 80 years and then it will happen. So now we did a similar thing over here. Okay, we said we will impose the most complicated test for our machine learning over here, saying that I will give you two images. This is generated, this is originally present, and this is a super result image which comes from my CNN over there, which is my machine which is generating that. And I ask this machine, I give you a pair of image, you tell me which whether it is real or whether it is not real. But then we played something which is called as relativistic test over there, which is the same as trying to play spot the difference puzzles. So you would see that there are two kinds of spot the difference. In one, you would have both the images on the same page, one beside the other, which is much easier to solve. In the other one, there would be one behind the other, or one at the end of the book, or even sometimes like totally upright at the end of the book. And they are the ones which are the hardest to solve. If you place something one beside the other, then it's easiest to solve. So we started doing that, and we actually gave this Turing engine one beside the other and asked it like, now solve this whole problem over here. So by way of that, this becomes more super critical because it can see 1:1 correspondences coming down over here. Now what this helps us in doing is that there is some amount of differences which are very perceptual, and we don't have a mathematical understanding of all of those differences over here. Now these Turing tests are basically neural networks which are again trained, they are also trained, and they train in order to be able to discriminate between these two in the best possible way. Okay. However, that does not solve everything. The problem still lies because a larger part is that WBCs or these white spaces, and they would appear almost the same in both the cases, and that drifts it up. So what we did is we came up with a suggestion where we said like, we will give you some region understanding, or what is called as a region proposal of where my WBC is present. And now what you are supposed to do is you compare between a pair of WBC and then tell me which one is a real WBC and which one is not a real WBC. That's it. And then you keep on updating yourself. So this Turing test keeps on updating itself. Now this becomes super critical in order to very accurately understand what is that relationship in the low resolution to high resolution of a WBC, because it does not need to cater to all the flat regions across over there. By way of doing that, we were able to create this CNN over here, which was given all the other information. And now what this guy's job was, this now started playing a prank on those two Turing tests. The prank it plays is, it will try to fool the Turing test to believe that whatever it generates is actually real. So the only time this can fool the Turing test to believe that whatever it generates is real, when it starts generating something which looks actually like the real. And that's the best case imposter syndrome which it can create. So that's essentially what this whole thing starts doing, and by way of that, through this whole process, we were able to obtain images which look very realistic as if they were on the high resolution. So look at a sample over here. The projection is already bad, but still you can make out, like here at least you can see some granules and some points over here, whereas this is a bicubic simple interpolation. You see it's very cloudy and almost washed off. Now you can take down something which is an SRNet generation before we did our Turing tests and everything. From there we got down these two, which are with the two Turing tests. Basically you apply only one of them versus you apply both of them. You can see that this one is much more closer to what this actual one at 40x looks like. So this thing is generated from a 10x image, whereas this is actually a cropped out version from a 40x image, and you can see how closer they resemble each other. Now similarly, these are on WBCs, these are on histopathology samples, and you can similarly see, like here it's almost like somebody did a water painting and then there was a jar of water which fell on that and everything got washed off. And you come over here, you would see exact textures even in these hollow lipid pools over there as well, which get preserved. So this is that interesting thing which we could come up with this. Now the next part is on the litmus test. What did we achieve by being able to do all of this? Because it looks wonderful on a set of data. We have a control data set. In the lab, everything works. Okay. So now taking up something from Professor Suman Chakravarti's day before yesterday thing, when he took it actually to the clinic, actually to a place where that does not even, there is no clinic which exists. But for my case, I cannot go to those places. I still have to go down to that guy who builds a microscope and give it to him, saying that, okay, now take it. Does your AI engine, which looks into these images at 40x in order to make a diagnosis, is it able to do an equivocal diagnosis by looking into super resolved images or not? This is what we said. So that's an experiment which we did over here. So this is that scanner from SIG tuple called as AI 100. Inside this robotic scanner sits all of this AI engine. There is a whole microscope, there is a super resolution engine, and there is a small drawer over here. If you look on the left hand side over here in the white box, which you can pull out, you can load a slide and slot it in, and inside that whole thing will happen and it comes out. Now we saw that these scale factors which you see, 4x, 9x and 16x, this is the amount of super resolution which you do, whether it's 4 times. So 10x to 40x. If it's 16x, which basically means from a 2.5x to 40x essentially over there. So if we move up like that, then there are different ways in which you can super resolve. One is a simple interpolation like nearest neighbor or bicubic. Then you can use some convolutional neural networks like SRNet or SRNet weighted in order to do that, and then we have this T1, T2 kind of stuff. Now what this essentially this number over here means is that if you run the original 40x slide through that AI interpreter, it will count some number of particular cells and everything. It will detect some pathological markers over there. Now the number of detections it had through an AI engine on the 40x, how many of them actually matched when we detected it through our super resolved version? So if the super resolution one matches very close to that, so say here it's 99.5 times. So there was a 0.5 drift. 0.5% of the times we could not detect it out, but majority of the time, 99.5% is a very high concurrence if you would look into that one. That from a super resolved also it found the same amount of pathological points which you could find in an original full resolution image itself. Now comes the interesting part. If you go to this one which is 16x, so 16x would essentially mean that your optical magnification is 2.5x, which means almost like putting a lens in front of the slide and looking through your bare eyes. It is that low resolution. So in 2.5x, I think in 4 captures or something you can capture the whole slide itself. From there we scale it up to 40x. Now there you would see that in the normal case it would have an 80% ability with just an interpolation problem in order to find out all of these specific cells. Whereas with our case it can go as high as 98% over there. Now imagine 16x means that it is 16 times faster as well to acquire. So we made something 16 times faster where compromise was just in under 2% on the performance accuracy, which is remarkably a different order in which you can get things done. So that's how typically in today's world we are trying to balance between optics, the complexity around that with speed, and how you can bring in more of compute, and where computational pathology plays a role is to get these things enabled, how better and better they can be. So this is the company which makes it. That is Tathagato somewhere over there, almost at the fag end, though he is the guy who leads all of this and he's the CTO for doing that. This is a company where they run physical diagnostic tests as well. It's in Bangalore. Both of them are in Bangalore, and in fact like it's 2 blocks away from each other over there. So if you walk up to human diagnostics, you can actually go and give a sample of blood and have a cup of coffee. By the time you have your coffee, you will get down a whole report coming down to you. This is that fast. And the difference is, like, if you try to do that same test in some other standard histopathology, some other pathology lab, that will take you 3 days in order for you to come. So now you can understand, like, where enabling compute made a blood test become as easy. And this was not that paper type blood test which Professor Suman Chakravarti was doing. These are like actual microscopic level tests which are not biochemistry. These are where you will have to actually count and look at cells and make an inference out of it, which still is a visual process. You cannot have any other way of doing it. And this breaks thing from a 3-day process to just a couple of minutes on the process itself. And that's a change which it's bringing on. Now, It has been a long talk by now. So I will end this part. This is about how we made something to really speed up a digital path system over here. The next part is where I would get into something which is more closer to my heart, where I would like to speak on non-invasive mechanisms of doing histopathology. And then this is a bit old, as old as my PhD and the time I finished my PhD. So half a decade old kind of things, but the interesting point is you don't have to take a biopsy. So now if I tell you this whole thing, that I will put a probe on your hand or stomach or liver or anywhere, and then I can tell you exactly what is the tissue composition underneath. But we will not investigate any tissue. I will not pull out a block of tissue and do it. Has anybody ever gone a biopsy done over here? Has anybody got a blood test done over here? Everybody. How does it feel? Painful. So now imagine if I am going to chunk out a 1 cubic millimeter of tissue from that location. Raw flesh being pulled out in order to do biopsy. So you can imagine how painful that is going to be. So we wanted to get rid of that, and I had a more interest because, I mean, cardiovascular diseases run in my family. So sooner or later even I will be diagnosed with one of them. I was pretty sure of it. The only problem which was there is that there is no confirmatory diagnosis for that, and I was really worried. Honestly, I will tell you, I mean, I started my PhD more of because there wasn't a confirmatory diagnosis, and possibly that's a good thing. Like, use public money, get your fellowship, and you design a diagnostic test so that at least there will be something available to test on you whether you have this or not. So that was all of my motivation. And then at the end of it, it led to something which is a diagnostic, a non-invasive histology of blood vessels itself. So you can look into every, almost in the order of about 20 microns on blood vessels, and at a 20 micron resolution you can find out what is the nature of tissue present in a blood vessel itself. Now where that makes a difference is when you have these plaques, or what is called as atherosclerosis, so you know about hardening of arteries. So people would have heart attacks. Now heart attacks are of different reasons, and in some of them there would be, you would be told that there was a bypass surgery, or there was something which is called as a ballooning or a stenting over there, which is of opening up the arteries itself. So what happens is that there is a lot of lipid, hard lipid, which just deposits over there and it clogs. So it's the same as clogging of a drain. So it just clogs over there because of deposits of these ones. So how do you understand exactly what is the extent of this deposition? So for that you need to find out something. Only way is like cut that tissue and bring it, but that will not be possible because you will have to cut your blood vessel, and that will restrict the blood supply. Anyways you are going to die. So in order to investigate, we just killed you, so we cannot do that one. So here the idea was borrowed down again from this old funda over here. So what was happening typically over here is that you have this white light which goes through this one, and then you get some colorful things over here which you look into it. So essentially if I break it down even further, what this would mean is that I have some energy which is going into this whole thing, which has a property which is called as, say, psi, and this is a physiological property of that one. Okay. Now what you are getting down over here is basically some other probed form of energy which you are sensing over here, which I called as chi. Now essentially the whole idea is that looking at this, can I infer about this one, which is essentially by looking at this, can I infer about this? And that's in a typical computational or analytical pipeline, that's called as an inverse problem solver over here. You know your forward observations, like if this is an input, that is an output. Given an output, can I comment on what was the input, or given an output-input pair, can I comment on what was the system which modified my input to give me that output? So any of you, if you have done, say, signals and systems or control systems kind of classes, you know there is something called as a system modeling. So my input is called as x of s, and my output is called as y of s, and my h of s is equal to y of s divided by x of s. So that's a kind of thing. So that's a property for linear systems. We don't have linear systems. These are heavily heterogeneous, non-linear kind of systems where it's not a straight line way of solving this one. Okay. So the idea was pretty simple. If I have a probe, an ultrasound probe, where there is only one element which is like constantly keeping on sending ultrasound pulses along over here, you would see this rotating, and then this keeps on sending on this top left hand side image over here, this part rotates. You are getting back some of these energies coming to you, and that's essentially what is this chi over here. and this F is essentially, this F is whatever is happening to this energy of acoustics, and your psi is basically the some physical property of that tissue, and that physical property of the tissue can be now related back into what is that tissue exactly. So the whole point is that if I have a computational framework which can invert this whole set of equations, then I will be able to find out what is the property of that tissue, and hence I can relate it to what is the tissue. So here you would see some red in the bottom left corner, this image, you have some red, green, blue kind of things, and those red, blue, pink, yellow colors are essentially different types of tissues, and how we had been able to find that out. So the trick laid in something which this gentleman P. Mohan Shankar had done during his research. So he was a guy from wireless communications who was studying a lot of indoor backscattering. So if you have two Wi-Fi routers, generally you find it troublesome to connect somewhere in between of them. There is a issue which creates up, and you have to, these Wi-Fi routers have to adjust themselves accordingly. So the whole algorithm which goes into this adjustment is what this guy had invented, and then he somehow figured out that ultrasounds also have the same kind of a problem, and then he started doing a lot of research on ultrasound. Now what he figured out is that if there is a acoustic probe, a pulse of ultrasound which goes and hits a set of tissues over there, then they will all start reflecting, and in a different way, and then what you receive over here, that echo, is basically a composite of all of the reflections over there. So essentially there is some sort of a statistical nature which comes down, and then he found out that if we essentially want to do this, then what I am getting is basically a composite of all of them, and from that composite I will have to infer what is the statistical nature. Now that's a problem. So if it's a point to point relationship, I can always find out, but if it's a composite, then it becomes hard. So getting back to the same question as in super resolution, if 1, 2, 3, 4, average value is 2.5, but from 2.5 I cannot exactly say whether it's 1, 2, 3, 4 or 4, 3, 2, 1 or 1, 4, 3, 2 or whatsoever, or 2.5, 2.5, 2.5, 2.5. That's the same problem which comes over here. So here, for that whole thing, for a lot of period of time, it was not possible to really infer back on the tissues, although this physics was well known. So the statistical mechanics of ultrasounds was known, but we could not infer anything out of that one. Now from there, what we did was something like this. So this was a mock experiment which I had done, and I can just show you exactly for just a notional purpose. What happens is that if these scatterers are quite far off, then you get one particular nature of a PDF, or a probability density function of these energy which comes back. When they are very close by, you have another nature. So you can pretty much see that the peakedness of this one, so whether it's narrow or it's very wide and dilated, is dependent on what is the spacing between these scatterers over there. Okay. So from here, if we get into this whole part over there, where it comes down is that if you look into different kinds of tissues, so this part is lipidic, this part is fibrotic, this part is calcified. These different kinds of tissues actually have a different spacing of the scatterers, and as a result of that you get this peakedness which is very different. So whether it's a narrow curve or it's a wide curve, and these things keep on differing over there. Now we tried making use of all of this. We said, like, let's look into these distributions over here, look at the histograms or something over here, and then infer back into what is the nature of a tissue which is present over there. But then there is another problem which comes down with all of decision making, which is there will be multiple of them which will come together, and there is something which is called as a co-located heterogeneity principle. So you have multiple sources which are contributing. So there are multiple random number generators which are coming down over there, and they have a very complex model. And this is typically a like infinitely summable, infinite component model which is not directly solvable. So from here, I mean, this took me 2 years to understand that this is the exact problem why nobody could solve it out. And then after that, we could figure out a way that you can actually remodel all of this problem into something of this sort, where you write down everything in terms of a different notion which is called as phi, which is now what is just a parametric distributions, just parameters of a distribution and nothing more. So instead of telling, like, I have a Gaussian with, so either you can draw a Gaussian with some mean and variance, or you can just tell that my mean and variance of a Gaussian is this much. So instead of drawing that distribution, if I just tell you the mean and variance, that is also the same amount of information. So this phi was essentially that mean and variance kind of a thing, which for Nakagami has some different parameters like gammas and alphas which come out. So if you do all of that, you will essentially be able to come up with this one. Now by being able to solve it out. Now what comes down is interesting is on the right hand side. If you look over here, on the right hand image you would see that there is a bright streak which is coming, and this is what is showing a calcified region in that tissue. Here you can see exactly which is the fibrotic region in the tissue. Here you can see exactly the necrotic region, and here you can see the lipidic regions over here. Now by way of this, what we could design is that now ultrasound machines, so typically in ultrasound machine you see a bunch of speckles like this which are very hazy in nature, but now you can tune on over there. You can select one particular, say I want to look only at fibrotic tissue. It will show you only speckles corresponding to that. It will not show you anything else. And that basically changes the whole game over here, because now you have the same tissue level information which you would have otherwise gone from histology, but now you are getting without having to do a biopsy over there. And that makes this whole investigation much more real time and much interactive in its own way. So the cardiologist does not have to rely essentially on a vascular pathologist in order to get back the reports and then make a diagnosis, but an interventional cardiologist then and there can actually look into what is the cross section of it histopathologically. So we did another study which was quite interesting. So we had a staged plaque. So there was a person who had different plaques in their arteries, and everything was at a different stage. So in one single sample you could get down all the stages actually, and then this is that interesting part. So this is somewhere in the intermediate lesion when you will not have a calcification or a necrosis set down. The majority of it is fibrotic. This is an atheroma stage when you have the first part of hardening, so you will have distinct calcifications setting up over there. Then there is fibroatheroma when you would see that there are solid calcifications as in over here in blue, and then you have some part of necrosis also setting in over here at the 9 o'clock position, and then eventually you go to this most vulnerable position when you have a lipidic pool which is very close to the internal boundary and it can rupture at any point of time. So this was that proof that you can actually stage across multiple points over there, and then in a very non-invasive way. It's not exactly non-invasive, it's minimally invasive. You have a probe to be sent inside a blood vessel, so there will still be a small pinhole kind of a surgery which has to be done on your body. Now we went beyond that, and what we did is that most of these models, what they were trained were with what is called as an in vitro model. So the person had already died, you took out the artery and then you injected saline and then you were doing everything. But then on a living person, how will it look like? That's the main question. So we actually took it down not on people but on rabbits. On living rabbits we had this whole thing done and saw whether, because the moment you remove saline and you put blood, there will be a lot of scattering which will happen because of the blood itself. So there was something which is called as domain adaptation which had to be put down. That was a separate work which we had done, and this is what was our engagement with Samsung in order to bring this closer from a lab scale thing to an actual prototype on a machine. And today a lot of Samsung medicine machines have a earlier version of this one where you can select tissue priority imaging over there. So they don't call it as tissue selective imaging but tissue priority. So it will boost up speckles corresponding to a certain kind of tissue, and that is based on all of this work which we had done over here in order to enable tissue specific imagings coming in. So that's all what I have to say, and then the later part of the work which I was telling, that's by a lot of people need to be thanked for that, and just like my supervisors and senior professors who were helpful in different points of time, and a lot of institutions which really played a role of being my host or giving me data for free, which otherwise would have costed a couple of $1 million in order to just acquire. And finally, thanks to the whole group of wonderful people, with Ronnie sitting here in the crowd as well. And then there are people who make this happen. So that's Francis, who was doing the super resolution work which I presented in the earlier part of this whole thing with microscopy, and how we built up a whole super resolution thing as well. So that's where I end, and now we are open to questions if you have any more energy with you.